let's look at let's study about the Riemann sum. Let's learn about what a Riemann sum is. So let me come up with a problem like this. X equals x squared here, and I only need you to draw that portion from the interval 0 to 1. So how about make a quick sketch of that, like similar to what I'm doing up here. Okay. I really have to make this picture. With that interval, so let me just sound like that. Right? It doesn't have to be the whole complete one. Okay. So go ahead and have a copy of this. A copy of that. We need this picture for a lot of activities throughout class today. If possible, I mean, maybe let's make a few versions. Same function over the same interval. I'm sketching about a couple of copies like that. Got that interval from 0 to 1. So I only need the graph over from 0 to 1. So the idea of the problem now is that think about a long time ago when people just started. There was need. That's why they came up with this problem here. We're trying to find, the goal here is trying to find the area, okay? The area that's shaded. So this is the area that I'm shaded here. See what I mean? Okay. It's not the area, I mean, doing area for a rectangle, that's easy, right? Length times width, that gets you the area. But nothing surprising about that, right? Getting the area of a... You guys still remember this kind of figure? Yeah, what do we call that? Okay, so what's the formula for that?
Top plus bottom.
Okay, top plus bottom. So how about the top is the E1 and bottom is E2, you mean?
Yeah.
Okay, so top plus bottom, and then what?
Top's height divided by 2.
What's the height? That's the height, right? Okay, divided by 2. Yes. So these are all what I so-called a regular figure. They got formula and rigid formula that we can use anytime. And then you guys went a little more advanced into the circles, and you got area of circles and all that, right? And then triangles. There's no surprise that we can calculate areas of triangles. Now, something like this, would not, right? We have a formula for that. See what I'm saying there? And really, a lot of mathematicians in the ancient time for a long time have to come up with something like this. Right? The area, not a rectangle, not a triangle, right? Something that's bent in some edges, right? And then the straight edge in some other places we get. Okay? And then you are getting ready for the kind of area later on that we go like through a region that's going around and all over the guys, not with corners or edges. So that's why we're going back to the really fundamental problem here. Just for that curve like this, and between the x-axis, right, and the curve, and then in that restricted interval, the shaded area like that, we want to find that. And so, in other words, we fail doing that. There's no particular formula for that. And so this is a plan of how they developed the idea over here. Just now, that's why I'm drawing it like a new picture over here. The target is to get the exact area. You guys follow me on that, okay? But now, in between the interval from 0 to 1, this is sort of like the total window over here. So I'm gonna break the interval from 0 to 1 into a certain number of subintervals. So the number of subintervals, let's call that n. And for now, for easy, let's just start with 4 subintervals. So I'm breaking it down. So now, that's how it's working. Okay? The total window right there, we're breaking it down to 4 subintervals. Now, the question arose here earlier, I mean, in the ancient time when they developing this. So when we break it down to subintervals, these are called the widths, right? So, in the beginning day here, do widths need to equal. Okay? And the answer to that was no. When you the original idea is that you don't have to make it equal width. So with 4 sub-intervals, you can make a long, some interval like that with, and then some other interval being smaller width, bigger, and then very small width right here, and then something like this. So they don't have to be equal width. That's what I'm saying, but you got 4 sub-intervals, clearly. And that's the idea of it. But then, as math become, as the idea become more trivial, equal widths are okay, actually. And equal widths are okay, and it will not change the result. And you will get this. You will get this a little bit later on about why equal widths are completely okay with unequal width. Okay. And so that's why, for simplicity, breaking it down to however number of sub-intervals here, you can always make the choice. Okay? As a choice, you can always go with the equal width size here. Okay? So that's why now, for simplicity, from 0 to 1 here, I'm going to cut it exactly in half, and then 2 more little halves, right? And that's how I'm having these sub-intervals. Okay? You guys follow what I'm saying right now? Okay? So the whole thing here, after breaking it down into 4 sub-intervals, the whole picture right here is called partition. Partition, because think about it, you got, as far as partition, now think in terms of the set right here, I'm using curly braces for sets, but the starting point of this whole interval is 0, so we call that x sub 0. It's also the value, the a, your interval, and then the first point, so right here starts, x sub 0, and then the first point right here on the interval, we call that x1. That's x1. And then x2 is right here on the x-axis. That's x2. x2, x3, right? The x3 is here. And then x4 is the last one for this interval. x4, which is also the last one in your interval. So, yeah, using the specific interval 0 to 1, but generally we're talking about any interval, any closed interval, a to b. That's why the starting point, x at 0, is your a, x at 4, the last one is your b point of that. So we call that generally as a partition. And so now in that way, remember, we purposely chose, right? We chose equal width. It's chosen. And okay to choose like that. So for the rest of the quarter, anytime that we're breaking it down into partitions like that, we're always going to go with equal width. So in that way, each of the widths right here, okay, each of those widths right there, we call that it's a delta x. Okay, it's a small. The interval itself is a small change in the values for x, right? So even that total window right there is a delta big and delta x. Now I'm talking about each one of these is a small delta x. Okay? And so delta x, in that case, since we chose equal width here, it has immediate consequence. Each of your delta x here, each of your width here, isn't it true that it's a 1 minus 0, the ending point of your interval, subtract the beginning point, right? And then we divide that by 4. You guys follow it? Right? So keep taking notes of that, and I'm going to have to, at some points I have to keep erasing some of these minor drawings and then keep adding some other details to that. Okay? And so that's called a partition. Let me put that away. So now, as a generality for the width here, generally delta x is always the ending point of your interval minus the beginning point, and divided by, see the 4 here came out from here. In this part, we chose 4 sub-intervals, right? And so here we're going to divide by n. You guys good at that? Yeah? Okay. So right now there's still a lot of explanation, so I have to blend in a lot of minor details in the figure. And then as we move on, I'm going to have to keep erasing these minor things and then go back to the brand new version of this picture over here. All right. Ready for keep picking up that idea? All right. So equal widths are okay. So now you got a partition in each of your sub intervals. Now this is the plan here. So I'm going to return to the nice clean version. I don't even want these dotted lines again. Right? But at least I got x1, x2, x3. Right? Of course, x4 is the last one, and x0 is the first one here. So, but now for some convenience, we have to set out a rule over here. The first subinterval, right? The first subinterval, let's call that. So now I'm talking about the first space here, right? Let's call it as delta x1. You guys following? Okay. And then that here is a delta x2. So now I'm talking the space between any two adjacent position points there. Okay. And then these are, that's delta x3. And then the last one here is the delta x4. Even though these are all equal size, right? They're all equal size right now, but I'm talking about for later on for other purpose. We need to reference each of those in particular. So that's why we have to call it, give them some indexing convention. Right? So delta x1, delta x2, and so on and so on. You guys see what that? Yeah? Okay. And now again, I'm going to have to erase the picture. Okay. So in each of your delta x, and you're more than welcome to redraw the new picture with each different labels for that. Right? So here is your, you got your in delta x1. So in your delta x1 right here, there are so many points in here in between, right? There's a point here, there's a point there, anywhere here. So you can pick just any point randomly inside of that first interval, delta x1. I'm only saying any point inside of that. I'm not saying exactly in the middle. I'm not saying in the left or in the right. Anywhere inside. You pick a point like that. You're going to call it as a sample point. So it's some x star point of this. Right? So as a name, is a sample point. Right? But what exactly is that? It's just some point that you can randomly pick or choose, right inside of each of your subintervals. And so in the first subinterval delta x1 right here, I choose a random point. I choose a sample point, so I call that the x star 1. You guys follow that? Okay? Right? And then in the next interval, yes, so the interval itself is a delta x2, right? But then I'm going to pick a point. See, the point doesn't always have to be the same with a similar position. It can be, like I said, just anywhere. And you can call it x2 star. It's another sample point in that subinterval number 2. Right? And then in the third subinterval, again, I'm going to choose, and when you're in an interval, and these are all closed intervals, you also have your choice to pick either the left-hand side or the right-hand side point as well. The left hand or the right hand of each of your interval as well. See what I'm saying there? So these are all the sample point. So, but I don't want to make the picture too busy. So in here, I'm going to pick the sample point really close to the right-hand side. Right? That's x star 3. You guys see what I'm saying there? Okay. And then on the last interval, yes, let's just pick the point again. Okay, and that point right there is x star 4. Sounds good then? So in the end, we've got a whole bunch of sample points. Right? These are all sample points. You see the idea how we come up with those? And then really, I said, you can pick the sample point anywhere inside of that, of each of those corresponding intervals. Right? And so in that way, again, there's no hard rule about where specifically you have to choose it. So that's why now you can start doing things smartly. So mathematicians in the past, this is what they've done over here. It's now in a brand new picture. Right? You're going to see that throughout class today. I'm going to have to draw the same picture quite a few times here. Right? So now you're breaking it down to 4 subintervals. 1, 4 subintervals. But now you can specifically. I made my picture way too upscale right there. All right. So specifically as left endpoint. So it's just, I'm talking about now the sample point that we specifically or we purposely choose a left endpoint to keep things simple and in an organized way. Okay, so to keep things organized. It's all about to keep the work, right? Keep the work organized. Right? And so this is what I'm doing here. So in the first delta x, call it delta x1, right? I'm going to choose the sample points right here. So this is where I call that sample point x star 1. You guys follow with that, okay? And so in that way, in that similar fashion, this is delta x2, that interval, right? So the sample point, needless to say, is right here at the left end point of your interval. You guys agree? Okay, so x star 2. Look good? Okay. And then, so on and so on, and delta x3, right? Your sample point is right here, that specific point there, x star 3, and so on. And then this delta x4, the fourth subinterval, your point is right there, right? Sample points. So the star thingy with the subscript is the sample point. Sounds good? Right? So now this is what we do. So with the left end point right here, remember you got this curve right here, some function, right? Now in our problem that I'm promoting right now specifically, it's x squared. Are we good with that, okay? So this is what we do right here. For the first subinterval, I'm going to substitute the sample point, okay, into the function. And then I'm going to multiply that with the delta x. Okay. Now, yes, I have to call that delta x1, delta x2 to keep them reference, but in the end, don't you all agree that delta x1 equals size with delta x2 equals size with all the way up to delta x4, right? Let's all call that the 1 delta x value. That's why I keep it simple over here. That's what I did. Okay, so I'm producing the function the function evaluated at the left end point, okay? And then multiply with the delta x there. Okay? But then think about the picture. The function evaluated at the sample point means what? It gives you the height, right? It gives you the height, and then the height here multiplied with the width right here, it gives you the area of a rectangle. And right now, because for this function specifically right here, by the way, so for this particular problem, your sample points is going to have to be separated. The first one is a 0 because we're choosing the left hand point, right? So for the first one right here, it has to be 0. So x star 1 right there is a 0. X star 2 has to be what? What's this point right here? 1/4. Is it 1/4? Yes. Okay. So 1/4. And then the third one right here, x star 3 right here, right? What's that point right there? Half. Yes. 1/2. Sounds good with that right there? And then that's easy enough to understand that because we set out for ourselves a rule that we're breaking it down, the total interval into the equal width, right? Equal number of subintervals, equal size, okay? And then from there we choose the left-hand side so you guys can easily track down those left-hand points on each of those subintervals, right? So what about the x star 4 right here in this particular problem? Anyone? 3/4. Yes. 3/4. Right? That's x star 4. Okay. And so this is what we're doing. Generally, the idea is like that. The first subinterval, right? We're gonna substitute. We're gonna evaluate the function at the sample point on the left, and then we're doing the same. The next subinterval. So I'm using the sample point x star 2. I'm gonna evaluate that into the function. Very similar to what we did for the first subinterval, and we multiply with the delta x. Yeah. So this time the picture will become more clear. See, delta x2 is right here, you guys follow? The left hand point is right there, but substituting the left hand point into the function gives me the height of that, because the function's height determines the output, right? And so f alpha, the sample point, is the vertical height representing the output. And so now multiplying with this delta x right here, don't we have a little, at this point right here, we have a little area right there. You guys agree? Right? It's got an area right there, shading that rectangle. So the height of this little rectangle, so now I call it a sub-rectangle. And you guys can hear, I keep accidentally say the sub-rectangle a couple times like that. That's the idea, because I already saw things ahead like that. But see, you got a width and a height of your rectangle, right? You with me on that right there? Okay? And then what do we do here? With the next one, similar thing. The function in the third interval, in the third sub-interval, I'm going to pick the star point, the sample point at the third interval, so x star 3, right? So x star 3, substituting that into the function, it's going to give me the height right here, above that. You guys with me there? And then with that, multiplying with the width right here of the rectangle, this is the picture that we have. Okay? It's another rectangle. Sounds good there? Okay? And so we multiply with the width. So now you have to understand as far as the impact, and I'm not making any connection between each one of these pieces yet. Right? I didn't say anything about each one of these pieces yet. What we do with them, but for each of the pieces, that's what we did. We multiply with the width of the subrectangle currently at, right? Multiply with the function's height here, evaluated at that specific left end point. Are we good with that? Okay. And so let's move on to the fourth one. Again, we're going to substitute. We're going to evaluate the function at that sample point. So it's x star 4. So x star 4 is right here, right? Evaluating that into the function, we have this height going up here. You guys follow it? Okay. And now multiplying with the width over, right? With that width right there, we're going to have a nice rectangle. And then I'm creating a shading for that rectangle again. Sounds good? Because we multiply with the delta x. So each one of these now as a picture, each one of these quantities here is as a picture is the area of a sub-rectangle. Am I correct? See, like that one right here is the area of that little rectangle we shaded here. That one with the star 3, right? That third rectangle. And they're all having equal width. We are allowed to do that legally. Okay. And now, so think about it. Back to our ultimate goal here. The problem in the beginning was asking, we want to find a shaded area. See what I'm saying? We want to find a shaded area, that nice and precise area right here. Okay? In this problem that we do it, we create some kind of area closing up. Yes, there are still some empty spaces here that we didn't reach to, but at least this is what we're doing right here. If we're adding all of these little sub-rectangle areas, we're going to get a what's so-called an approximate, right? See what I'm saying? Now we're going to have an approximate. So all of these here is going to be approximately closing up, right, to the actual area. Because right now we still didn't know what that area is. All I know is that I can do some sort of like a trick around. See what I'm saying now? Like a playing around trick, some working around, and I'm getting to some approximate of the area. It's just the sum of these sub-rectangle areas. Sounds good with that? And so specifically with this function that we're looking here as our particular problem, that the area now specifically is approximately calculated by, see, f of x star 1 is going to be, what we did here is a function is going to be 0 squared, right? See, x star 1 is right here, 0. Right? Yeah, see what I'm saying now? So we're substituting that into the function. That's why I'm having the square. Sounds good? And then we multiply with the delta x here. In our particular problem here, remember, delta x is 1 minus 0 over 4, right? Which is 1/4. You guys repeat that? So now we're going to multiply this height with the width, 1/4. Right? That's the area. So the next one here, we added with the next rectangle area. So that height there is going to have to be 1/4 substituted into the function. So 1/4 squared multiplied with another 1/4 being the width. Good for that? Okay. So this is the work we're doing for this specific function, the x squared. This is the generalization of that, right? The generality of how the idea works. Okay. Sounds good. All right. So let's continue. Now it's going to be the third one here. It's going to be 1/2 for that sample point. Right? We square it, we evaluate that into the function, multiplying that with 1/4. And I'm running out of space here, so I'll have to write it down in the next line here. But the last sample point is 3/4 square, right, times the 1/4. That's it. So now we have some actual numerical answer, right? Some numerical result here for this function. So here we only have a general formula. But here we really push into doing some work with that. All right, so you guys go ahead and do the calculation for me. Go ahead and tell me your answer right now. We can double check. 875. Right. Then wasn't. All right. So, but now, so we've got to some answer. Fractions or decimals, but in the end, this is only, you got to understand it, it's only an approximate, right? And what have we done here? We use 4 subrectangles, 4 subintervals, and then we produce rectangles based on the left endpoint. See what I'm saying now? Okay, so ladies and gentlemen, this work that you're seeing in front of you, the general formula right here, is what we call the Riemann sum. So let me write it down in a more general setting right here. That formula we wrote down the function value. The x star now being specifically chosen as the left-hand point. I'm going to say in the first interval, right? We go the left-hand point. So instead of x star 1, I'm going to go xl over here for left-hand point. So indicating in the first interval, you go with the left-hand point. You multiply with the delta width, delta x, yes, right? And then plus, and then the function value. Function evaluated at the left endpoint of the second interval. So that's why it's XL2 again. You guys good with me on that? Okay. And then that gives you the height. It's giving you a height multiplied with the width. Uniform width, right? Equal width. Yeah. And then we continue in this until the end of our interval. I mean the last sub-interval here giving me some x sub n here. Are we good with that there? That's a generality. And then the left endpoint multiplied with delta x. So, ladies and gentlemen, we call this thing right here, this whole, it's a sum, right? We're adding things up. It's a sum, right? Yes. So we call it, it's a left Riemann sum. Okay. Sounds good. You're creating subrectangles, right? And then subrectangles, and then each one of these you can think of that geometrically as the area of a subrectangle, and we're summing up those with a subrectangle, so we call it the left Riemann sum. And so for that, it's a Riemann sum, and they're choosing the left endpoint. And so people, over years, over generations, they come up with a short notation like a capital L over here. It's indicating a Riemann sum, capital L, using n subintervals, right? And then when people see L, they will know that it's going to have to be the left endpoint specifically chosen. You know what I'm saying, huh? Right? But that's what I call the left endpoint Riemann sum. And then that area here is specifically n subintervals. And so now, of course, these days, needless to say, those subintervals are all allowed to be equal width. That's the number one thing right there. So I will never have to repeat that again, hopefully. Okay, so from now on, this point on, your work, anytime that we're doing Riemann sum, we will always go with the equal width, even though the original idea didn't require equal width. Okay, but to keep life simpler and to keep things less complicated, it's completely okay to go with the equal width. And then choosing the left endpoint specifically for some good purpose, we're going to go with that and come up with that formula. But now there's still some more further details in this formula that I want you guys to understand a little bit more. So think about. So now specifically, I'm talking about a delta xi, for example, right? A subinterval. In that picture that I still have right here. In the picture that I still have right here, like a delta x1, delta x2, then any of these delta x, if you're looking at the delta x2 right here, the difference, it's a delta, see, delta means difference, right? So a delta here is the difference between x2 minus x1, because we call that point right here x of 0. Remember from the earlier picture that I drew down right there, the very first point right here of your total window right there. we call it x of 0. Okay? And so this is x1, x2, x3, x4, those partition points. Okay? And so the delta x2, for example, has to be x2 minus x1. I'm not talking about the sample point anymore. I'm talking about rolling back to the partition point. Okay? Right? Then that's what I'm looking at. And so now as a generality, then any x of I, when you break it down into n subintervals, and the width at the interval at any I interval is going to be x of I, right? The partition point x of I minus x of I minus 1. That's one thing to remember. You guys follow me on that, okay? But remember, they are not the star version, okay? They are the sample point that defines your subintervals. You guys with me still? Right? And then that's one information to remember. And then, yes, any delta x here is e minus a, right, over n. So now in that way, I'm going to really have to draw a picture over here. Think about an interval, a, b, right? And then you're now attempting to break this down into multiple subintervals, right? And then of course we already assume that these are all equal widths right here, because delta x equals b minus a. And so a here is x of 0, right? It's x of 1, x of 2, and so on, right? And then this one right here is tentatively your x of n, depending on how many subintervals you want to break it down. For easy, I always go with 4 a lot of times. Now, what I'm saying here is that, so the very first left-hand point, now I'm talking about the sample point version right here. Instead of star, because we already knew that we chose the left-hand point, we're working specifically with the left-hand point. And so that has to be x of 0. You guys agree? Right. And then, what about x2, xl2 right there? On that second interval, it's going to be equal to x1, right? We good with that so far? Cool. But then x1 is related with x0 by the x of 0 plus with the delta x over. This is your xl1 right there. That first sample point is also the left-hand point. You guys following that? And then we'll be moving on to the next one right here. This is xl2. Agree? But xl2 here is that. So now we count it back from that initial point right here. That that's going to be 1 delta x phasor over to the right-hand side. You guys agree? Okay. And so now in that way, let's do some more math right here. The left-hand point on the third interval, right, is, yes, on the picture here, then it has to be x2, right? It lands right on x2, yes, nobody argue about that, but then the point now is that it's the same as x0, the starting point, but plus 2 times of the delta x over. Because right there, it takes 2 spaces, right, to reach to that point from the beginning point x of 0. You guys would need that. Okay? And so just like that, xl4, right? Yes, you can see that it's going to go x of 0 plus 3 times the delta x. See what I'm saying now? So, are you guys seeing a generality here? My board is getting admittedly a little busy, but from what I'm seeing here, let me clear out all the all the detailed development work right here, but in the end, we generalize the following result. When you're at any specific or any left-hand point at any generic interval, right? At any I interval generally, and it's going to be always x of 0 to the beginning of your total window, right? But you're going to add with I minus 1 times of the space delta x. Okay. You guys agree? Right. Just like how I said earlier, hey, when you're looking at the left-hand point on the fourth interval, right? It was the x of 0, and then you added 3 times of the delta x. So 3 times here is 1 less than that current the interval's index. Okay. Agree with me on that? Okay. So it's a generality about any That's what we agree about the generality of those left endpoint Riemann sum. Sounds good? All right. But then in the end, that's how, see, this is general formula, but this is one important information that tells you how you can determine generally any left endpoint, right, at any interval, at any ith interval, when you're breaking it down and using the left endpoint rule. See that? All right. And so, let's put that there for now. The same picture. See, when it comes to this, there's never been, I never had enough board space to draw all of these details here. Right. Same graph. That's just for simplicity, breaking it down to 4 subintervals. Right. So n equals 4 here. This is our x of 0. Right. x1, these are the position points. x2, x3, x4, right, which is also 1, the any value. Good. So this time, let's look at, because it's all about the sample points again, right? The sample points, like which point in each of these, which points in each of these subintervals that we can pick. So we can now look at right endpoints. Right? So in the first interval, I'm going to pick again. First interval, I'm going to pick a sample point x of 1 star. But the sample point this time, I want that to be the right endpoint. You guys following? Right? So this time, to make it special, I could have done this when it was earlier in the left endpoint as well. The right endpoint this time on the first interval is right here. Don't you guys agree? Okay. So let's do that work at the same time over here. So as far as the sample point, but now we know our goal here is to get the right endpoint. Then the first right endpoint here is going to happen at a 1/4, right? You guys agree? That little red dot that I put, right, that aligns perfectly with x1. So x1 is a position point, but we choose that the sample point on the first interval is right on there, okay, or right on the right endpoint. That's why it's called right endpoint, right? And so what's the next right endpoint? So this is x. So now I'm going to call that xr1. Sounds good? It's a sample point in the first interval. And just like that, the exact same picture that we've had again, delta x1 is here, delta x2 is here, delta x3, and delta x4, right? But for the first sub-interval here, I'm choosing the right endpoint. That's why I call it xr1. Just like similar in how we call those xl1, xl2, and so on. Okay. And so the xr2, needless to say, has to be right here. xr2. Are we good? And xr3, right? xr3. Look at that. And then so this time right here, xr4 is going to be the same, exactly the same as 1, right? Just this particular point. Right? Sounds good? Because in every one of our subintervals, right, we're going to pick the right endpoint as a purpose. Okay. And so now if we're breaking it down into specifically for this interval, then the right endpoint is going to be 1/4 being the first one, and then the 1/2, right? And then there's a 3/4, and what's the last one? 1. You guys following? Right. But now what I'm doing for the right endpoints, right? These generally as a sample point, I'm going to evaluate the sample point into the function. Multiply the same thing right here with the width delta x that we have already previously calculated. Okay, so that gives me, so this time here's how the picture looks. The first interval, but we're gonna rise some rectangle, right? But then the height of the rectangle this time is gonna be like this. From where the sample point on the right hand point to here, we're gonna rise some height here. Following? Okay? But then this height right here is gonna go like this. A little bit over the curve, right? A little bit above the curve. It all depends on how the picture of your current curve is. So right now in our situation with this function I'm working with, f of x being x squared. And we have the first rectangle over here rising a little bit above the actual curve. Sounds good? But now doing that same, once again, height times width right here, we got a what so-called area of that rectangle. That's first rectangle. You guys agree with me on that right there? So please feel free feel free to draw your new picture right here. You have to. Don't try to blend like left hand side and right hand side picture into one same graph again. It's gonna make your graph really ugly. Okay, I've seen some people doing that before, and it turns things into a mess. Okay, and so in the next rectangle over, in the next subinterval over, we're gonna go right hand point. Right, again, it rises the height for us right here, because that's what f, the function evaluated at the sample point in the second interval, is all about, right? And so that's what it is. Multiplying over with the delta x. So now multiplying with delta x, what do we end up here? A rectangle area again. See that? Okay, for that specific little area, that little rectangle. And then on the third rectangle, again, x star 3, right? I'm going to, that sample point, but now remember, keep in mind, it's already the right-hand point under our work right here. So we're going to evaluate that with the function, and multiplying that height with the delta x, same width right here, right? So from here, the height this time is going to be generated by this. And so multiplying with the delta x over, we have that is understood, right, as the little area that we're looking at. See, my picture is already getting busy, and it's blended with all of these drawings that I made earlier. Right here, that's how x or 3. Good. Then the last one here, the sample point is now being chosen to be the right-hand point. Right? But generally, I just keep calling that x star point. Then multiply with, evaluate it into the function, multiply with the width, delta x. I got another area. This time the rectangle goes like that. See it there? Right? And this time, just the way how our function looks, right? Any one of the rectangles here is going to go a little bit above the curve. See what I'm saying up? Right. But now, adding all of these together. So, of course, each one of these is a little areas, right? So summing up all of these areas right here, we got some kind of total area. That's the sum of all these 4 little shaded area from the rectangles. But does that really come to the answer of that area that we drew right there on the other picture? It's just maybe close enough, right? But it's still a little under. It's still a little over. So our actual area is here. Okay. But then those rectangles right there, this time, choosing the right-hand point, we created something a little bit above like that. But again, we've got all of that as approximates. Is a good, we can use that as an approximate to our actual area. So our real destination, we still didn't know the real answer. But the real destination right there can be approximated by this sum. Sounds good then? And then into the function, into the actual function this time. You see the right-hand point, the first right-hand point I'm going to go with in our functions being the f of x equals x squared. So we're now looking at the area, right, can be approximated by, so the sample point 1/4, I'm just going to square that and multiply with the delta x right here, is again 1 minus 0 over 4, right? Multiply with 1/4. You guys with these still? Okay. And then the next one here, again, it's going to be a 1/2, so I'm going to substitute that or evaluate that into our function, multiply with the delta x, 1/4 right here. And the third one right here is going to be a 3/4, square multiplied with a 1/4. Right? And the last one here is 1 all square multiplied with a 1/4. Right? So go ahead and use your calculator. Get me fractions and then at the end give me decimals. But get me fractions first. Okay? Go ahead, take your time. Fraction?
I got 15 over 32.
You got 15 over 32. All right. It looks reasonable enough. And then with that, what's your decimal right there out of that?
0.46875.
46875. Right. But this is again, we only using that as an approximate to the real area that we're looking at again. So now again, let's just formulate this. So what we've done there, right? The work here specifically now chosen. We choose the sample point to be the right hand point on each of our subintervals. here we're looking at the function evaluated at x1 r, right, or xr1 that we multiply with the delta x, and then we're going to add that with the area, or just the function value at the sample point on the right hand side, xr2 delta x, plus so on and so on, up to the last one here being f of xr n. That's assuming we're breaking it down to n sub-intervals, right? Multiply with delta x. Yes, we call this right here, sum right here, call it this time it's the right Riemann sum. Right? It's the right endpoint Riemann sum. And then specifically of n sub-intervals. Just like that, notationally we're looking at this is called R or N. Right? That's how we break it down again. Then this time, think about our partition. X0 is here the same with being at the beginning of your interval. Xn is here the same as your endpoint. Breaking it down, then the right endpoint is here, right? So this is x r 1, which is the same as x of 0 plus a delta x over. See what I'm saying now? And then x r 2 right here, which is the same as x of 0, but plus 2 delta x is over, right? 2 delta x is over. And so generally speaking, the right hand point at any subinterval is going to be x of 0 plus I times the delta x. Sounds good? Okay. It's a general, sort of like a regulation, the way how we're breaking it down is those sample points. And then each of these delta x is again b minus a over n. That was in the written out form. It's going to be the function for the first term is the function value at the right hand point. So that's why it's the xr, the right hand point of our first interval multiplied with delta x. Then the plus, then the function value at the right hand point on the second interval multiplied with delta x. Plus so on and so on. Last term here is going to be the function value at the right hand point on the nth interval. Okay. Multiply with the delta x. Okay. So that's the written out form. Then again, in summation notation, or n here is going to be sum, right? Indexing from I equals 1 to n, summing up all those terms from 1 to n, that's what the indices apart. And each term here is going to be generally the function at the right hand point, right? The function evaluated at the right hand point on any I interval, multiplied with delta x. Okay. And that's how we're formulating the right hand point, the right hand point Riemann sum. Okay. Two different ways of writing that. Right. Endpoints. Okay. And then we came to, and then for each one of these, right, for the left hand point right here, of course, for any of these, then delta x, again, as a reminder, delta x is going to be the final interval minus the final point of the interval over minus b minus a over n. And subintervals. And for the left hand point, each left hand point right here that we're looking at, the left hand point at the either interval is really the x of 0 plus I minus 1 times delta x. Remember that development I've had from the earlier lecture? Okay. So it's worth to note it, writing our. This is the left hand point Riemann sum. This is just the way how we regulate the left hand point based on the x of 0. So think about your total interval right here from a to b, right? And this is always x of 0 being a. And then breaking it down to n subintervals, so your B point is x sub n. So whole bunch of intervals, right? Whole bunch of subintervals equal size here. That's why delta x here, each one of these is a delta x. Agree with that? Okay, so that's why left hand point is there. So pick this interval, for example, right? Some I interval. Interval. Right. And so the left hand point, that's why it's gonna be. Right now we at the specifically here 1, 2, 3, 4, 5. Right? The fifth interval, for example. Then it's gonna be this left hand point right there. It's gonna be x sub 0, right? Plus only 4 times the delta x 4 spaces over. That's the idea right there. That's why it's I minus 1. Okay. And then now in that same way, it allows me to now erase this minor right there. And we've come to that general regulation that for right hand points, right? Using the right hand point sum, and each right hand point on each subinterval is going to be the right hand point on the I interval is going to be x sub 0 plus I times base delta delta x. Okay. And so now I gotta emphasize one thing. I started out with that area problems, right? But you gotta remember, or I have to emphasize now that the Riemann sum came out not only for the area purpose. See what I'm saying? A Riemann sum on its own is just simply a Riemann sum. We got that definition right there. But so now Riemann sum. What I'm trying to say is Riemann sum, right? It's not necessarily, right? Necessarily for calculating area. You know what I'm saying? No? It's not really for. Outside of calculating area or approximating area, it can be for a lot of other stuff. Again. Okay. So the Riemann sum on its own is just a. So the area problem is only an application. Approximating area, like how I've been starting out with that. Approximating an area is only an application, okay, where we apply the idea of using the Riemann sum. Okay. Okay. But the Riemann sum on its own simply is just a Riemann sum. Okay. And then people define that. All right. So now, after taking this understanding right here, and so now I can take you guys into an example. Okay. Sometimes you may call that using 8 approximating rectangles and things like that, right? Okay. The left-hand point we want some. 8 subintervals with the left-hand point we want some. So we're going to have a part B later on, but let's for now work on the problem here. All right. So we definitely have to have a picture of that, right? And your function 1 over x plus 4, so we have an asymptotic vertical line right here, negative 4 somewhere there, right? I make my scale again. So it's going to be like this. That's our function. Sounds good with that, okay? Okay. And so the interval from 0 to 5. Okay. I made 5 a little too far. About half of it. That's 4. 5, just about right here. Okay. Right. So 0 to 5. 0 to 5. This is the area, the shading area we do here. We want to approximate that area, right? Using the 8 subrectangle function. See what I'm saying? That's the area. See? Does that match with the description? Under the curve, right? Under the curve. And of course, needless to say, it's between the x-axis and the curve. That's why it's under the curve. It's a one famous term right there that people later on will use a lot. You guys will be a lot of times exposed to that. And then the between, right, from 0 to x equals 5. That's why I'm restricting that into the shaded area right there. Okay? That's our area challenge. And so, after you guys took a picture, so that's the precise area, but unfortunately we didn't learn the tool to get that precise area yet. See what I'm saying? That's why we now have to do approximated work, right? So I'm going to create a zoomed in version, the reconstructed picture, because now you have an idea of what that area is. I'm going to have to create a real zoomed in version right here. So the real zoomed in version is going to go like this. Okay? Fair enough? And so now, from 0 is here to 5 is here, right? That gigantic space here, we're going to break that down into 8 subintervals. So it's easy to divide by 4, and then from there on, we cut each of these in half. And of course, so now in these days, all of our units, all of our spaces here between the subintervals, right? Those are all equal size. Okay? So that's the one part that's keeping life simple for us. Okay? So with 8 subintervals, now we can do a quick little math right here. The number one thing, delta x is going to be 5, the ending of your overall window, right? Subtracting 0, divided by 8. And so the delta x here is being a 5/8. You guys follow it? So now let's think of that. So if it's a 0 here, and this is the first 5/8, you guys agree? This is the partition point, right? 5/8. The next one right here is going to be a 5/4. You guys agree? Right. The next one here, we 3 times that, so it's going to be a 15/8, right? So with this partition right here, then we're using the left endpoint. So now you can go ahead and indicate your left endpoint, because left endpoint or right endpoint will land those sample points right on those partition points, right? So for the first interval, this is going to be, this one right here is going to be our XL, right? 1, because that's the first interval. You guys follow it? Right. And then there's a XL2 right here. And then right here is XL3. That's one thing of that. Because on each of the interval, first interval, second, third, right? And we pick the left endpoint. Okay? And that's how we're going with that. So generally, again, I remind you that the left endpoint of any interval I, right, has to be x of 0, which is this case here. This guy is 0, x of 0. So we get it out of the photo window. Plus I minus 1 times of the delta x. That's how it works. Right? And so now we're ready. So the left endpoint Riemann sub, right? We want to approximate. You guys see that? Right? We want to estimate the area using the Riemann sub with 8 subintervals. And so that's why here's how we can logically write it. The area, the precise area that we don't know yet, right, can be approximately equal to. See what I'm saying? No? Equal to what? Equal to L8 here, right? The left endpoint using 8 subintervals, and left endpoint Riemann sum using 8 subintervals. And so now from this point on right here, we're going to go ahead and calculate out. So L8 itself right here, the function is going to be f at. So now let's write it down and let's not beat around the bush anymore. The first left endpoint is 0, right? So it's going to be f of 0 times the delta x, in this case being a 5/8. You guys follow it? Right. And then we're adding the function value at 5/8, the second left endpoint. Right. We multiply with 5/8. We good with that still? So this is the height. F of 5/8 is going to give me a height. And this is just the delta x quantity, right? And then plus, so on and so on. So now the next one here we have, so we are expecting 8 terms altogether, right? So the next one here is going to be 5/4, f of 5/4, multiply with 5/8. And the next one here is going to be plus f of 15/8, right? Multiplying that with 5/8. I mean, for this one time right here, I'm purposely rewriting the whole Riemann sum rule right here. That's why you can see I'm writing the tedious common factor of 5/8 and 5/8. But later on, you have your choice. You write that as a common factor. That's all you factor it out. See what I'm saying? That. And then plus the function value at 5 halves, right? And how many terms have I had so far? 1, 2, 3, 4. This is only the 5th one right there so far. Times 5 5/8, right? And really, I'm almost running out of space right here. The function value at I have so 5/8 times 5/8, right? Plus function value at 15 quarts, right? Times 5/8. And the last one, we got to kind of jump up a little bit here. Plus, the last one is f of 35/8 times 5/8. All right. So now we're going to do the calculation on top of that. So now you guys have the calculator. This is the part where you definitely need to help me out. Okay, our function is f(x) equals 1 over x plus 4. And so for your real work right here, you only need to do each one of these. The f of 0 plus f of 5/8 plus, and then after the adding, you're going to multiply with 1 common 5/8 to this, right? It's the way it is, common factor, right? So that's just the writing down work right there, but when we're doing the work right here, we can be smarter than that. See what I'm saying, no? Okay. And so f0 plus f of 5/8 plus f of 5/4, so on and so on, right? And then in the end, after adding up all of those, we're going to multiply with a common factor of 5/8. Okay. So I'm going to wait for some answers. All right, so we come to this. So after adding up, right, multiply with 5/8 right here, then we're looking at the final area. It's approximately equal to 0.85596 here in 5 decimals. But, yep, this value right here is our LCA. So I'm with that. Yep. So that's the work that we're doing. And then for the next problem, it should be I should be able to get it faster with that. All right. So for the same example over here, let's look at part B right here. So this time we want the same area again, same interval with the shaded area, but we want to approximate that with the right-hand point. Okay. We want to go with the right-hand point Riemann. That's the area approximated by this time R8, like 8 subintervals. So now I'm going to have to redraw my figure here a little bit. Adjust them. 5/8 now is going to be our right-hand point on the first subinterval. This is the right-hand point on the second subinterval, and so on and so on. So this time right here, we're going to make use of that common factor nature. So I'm going to have a 5/8 being the delta x, right? Multiply out front here, and in my brackets, I'm going to just have f of the first right-hand point is a 5/8. I'm going to add with f of the next one here, 5/4. And the next one here, f of 15h plus f of 5/2, 4 more. The last one is right? At least I have more space to write this on. So I hold out that common factor right there. Okay, so go ahead and do that R8, do the calculation. Just adding up all the function values, right? And then multiply by a common 5/8.
I got 0.769155.
You're pretty good. Yes, that's the one. All right. So the area that we've had here, so it's just using the calculator. So the area approximated by that value. So this value we are about to write out, that's R8, right? And that's how we're calculating it. So 0.769155. Fair enough? That's the value for R8. And this R8 right here is the closing up estimate for the area. Sounds good? Okay. And so, as far as the Riemann sum, learning about the left endpoint and the right endpoint Riemann sum, that's not the only way. Because in the end, remember from my lecture from our earlier lecture when I was introducing about the Riemann sum in general. Right, let me go back and erase out this word right here, because that's still long enough. So I'm going to just quickly review you guys with the general formula here then. Yes, for the left endpoint, right? And some interval, the Riemann sums go to the function at the left end on any I interval, right? And multiply with delta x, I indexing from 1 to n right here. And then for the right Riemann sum, okay, right endpoint Riemann sum, we're looking at the function value, evaluated at the right endpoint on each I interval, multiply with delta x. So these cases, in the end, let me remind you, any one of these cases generally come out with a Riemann sum in general, right? A Riemann sum in general that I introduced that yesterday, but I didn't really enforce that. The Riemann sum in general, because remember when I was saying we got an interval and we break it down into some n subintervals, right? Then picking a sample point inside each one of these doesn't have to be strictly just endpoint or right endpoint. See what I'm saying? No? It can be just anywhere inside of that. So this is some x star 1 right there. This is some x star 2. Remember the idea right there? Right? And they don't have to be at a specific location. And so, in general, the Riemann sum here is going to be the function evaluated at some sample point x star in each of the I intervals. Okay? Multiply with delta x. And yes, we already wrote it down to the simple case that the delta x is simply just equal signs here for that. So that's a general Riemann sum. But now, left endpoint, right endpoint, right? It's just a choice. So think about it. You also have this time there's no sample points there. You have your choice to pick the sample point to be exactly in the middle. See what I'm saying now? Exactly in the middle. It works too. Instead of left endpoint, instead of right endpoint, instead of some point being closer to the right, we pick exactly in the middle. Okay? So that's general sample point now. For the first interval now becomes xm1, the midpoint. See what I'm saying there? Okay, and then in the second interval, I pick the midpoint again, and I call that it's x, the sample point in the middle, xm, in the second interval. Okay, and then so on and so on. We can pick the middle interval, x, m, 3, and so on and so on. And so, yes, ladies and gentlemen, we can also go with what's so-called the midpoint rule as well. So we got left endpoint, right endpoint, and we got midpoint. Okay. Midpoint rule. Good. So the midpoint rule goes as far as the sum. The Riemann sum here is a capital M with n subpartitions. We go the function value at the first midpoint, right? Multiply with delta x plus the function value at the second midpoint, right? Plus etc. times delta x and plus etc. to the last one here, the function value at the last midpoint, and multiply with delta x. And then in the summation notation, we're looking at m, the Riemann sum, the midpoint rule with n subintervals here. So summation I from 1 to n, and the function at the midpoint rule xm of any I interval multiplied with x. Okay. That's the midpoint rule over here. And so in the end, the midpoint rule, how do we determine the midpoint rule? So on each interval, again, I have explained the other day. For each of the interval right here, this is delta right here. This first interval is delta x1, right? And then it came out from x1 minus x0. So the very left point right here is x0. And so now the midpoint in the middle of that first interval, midpoint 1 right here is going to be x1 plus x2 with x0 over 2. You guys remember this formula to find a middle value between two values on the line of number. Right? And then just like that, right? Midpoint number 2 right here is going to be, midpoint number 2 is x2 plus x1 over 2. So now generally I'm looking at any midpoint. The midpoint at any general I interval really is going to be the I sample, the I partition point plus the I minus 1 partition point. We add them up, we divide by 2. That's how we obtain any midpoint. Now for this particular midpoint rule over here, applying that in this problem is a little too much. So I'm going to call it example 2. Here for this example 2 being brand new right here. Same function even though same area that we're estimating it. Alright. So we've got some curve right here, x0, 0 here, 5 is here, right? But using 4 subintervals. We only do these. Sound good? Okay. So this is 5. So the delta x right here in this case, right, equals 5 minus 0 over 4 is 4 subintervals. That's what the 4 here is for. 5 fourths. This is 5 fourths, right? 5 halves, 15 fourths, right? That's why here it's back to these points right here that we already had in our partition. The first midpoint here was 5/8. Right here was 5/8. You guys follow it? Right. And right here, that red one right there, it was 15/8. 2, 3, right? Fourth one right here, right? So now for calculating M4, we've got 4 subintervals, and the midpoints are being written in red ink. So in the end, it's just the same picture, right? So now this is what we have right here. So the area is approximated by M4, right? And yes, you know what? Let me just write down the complete one right here. The function at 5/8, midpoint in the first interval multiplied with delta x, being 5 fourths. Second term, the function value at 15/8 multiplied with 5 fourths. Third term, the function value at 25/8 multiplied with 5 fourths. And the last one here, the function value at 35/8 multiplied with 5 fourths. Okay. Yes, and then you can, in your real-time calculation, you can factor out the 5 fourths, right? And then go f of 5/8 plus f of 15/8, right? Plus f of 25/8 plus f of 35/8. You're ready for the final calculation. Got the answer here, and then you guys can go ahead and finish that and double check that on your own time at home. Okay, outside of class. But the answer will come out after this. For the M4 here, that's gonna be 0.40386. Okay. That's the answer I've got for my calculation. But maybe I can also type it in incorrectly right here. But then that's how much we can approximate our area with. That's approximately equal to the actual area. Yes, we want some work. It's tedious and a lot of effort. Yeah, but that's how it's done.